All right, so let's get started, folks. My name is Dr. Pat Kiley, CEO of Sentry. Really happy to have people here. I think we have, 25 people registered for this, so people will probably jump in as we move through this. Just maybe a 2-second background. Sentry, we've developed bio-electrode sensors that monitor and measure the consumable BOD in wastewater in real time. We have 170 plus deployments globally, and where our sensors work best is at the very front, the influent of a wastewater treatment facility. So we're very good at measuring how much BOD is being consumed by your biological treatment facility before that wastewater actually enters your aeration basins. We use that signal for most of our customers to flag and alert problem conditions in wastewater. And we've been doing this for 4 or 5 years. Some of our customers, we have 4 and 5 years of data. And how we've done that typically has by using threshold alerts. So a high alert, too much BOD, a low alert, there's something toxic, there's something that's going to upset your biomass. And Cash today and the technical team that's led by Jack Ambler, our CTO. Cash is a client manager and data analyst with Sentry. He's graduated from Dalhousie University with a master's in chemical engineering. Cash has been working with Sentry on advanced statistical analysis and machine learning protocols for the last 2 years. And Cash is passionate about helping us alert our customers to these problem wastewater events in a better way. Threshold alerts, high or low alerts work well. They pick up some, if not most of the alarms. But if we can leverage these 3, 4, 5 years of data with our customers, using these new machine learning algorithms, we can flag all of these events for our customers. And that's what Cash is going to go through today is some of his learnings and some of those improvements that we're going to be launching with our customers in the coming months. So with that, Cash, do you want to take it away?
Sure. Thank you very much for your introduction, Pat. I'm Cash Barry, Client Manager, Data Analyst at Sentry. Welcome to today's webinar on instantaneous detection of problem wastewater condition, integrating bio-electrode sensors and anomaly detection algorithms. So at the beginning, I really want to go over why we are here today. So as many of you know, the quality of influent wastewater can have a significant impact on the process, treatment and efficiency of the treatment. So we have been collaborating with Bill Peoples and Town of Coburg for a while. They are mid-sized municipality wastewater treatment plants, and they are interested to know what is coming into their plant, if they can do anything about the events that are happening at the influent, and how will those influence characteristics are affecting the process treatment. They have a specific problem statement regarding this discharge of industrial to their influent. So it is consistently affecting their process treatment efficiency. They're over aerating the tanks consistently, and it is also affecting their final effluent. So we are looking to implement Sentry and event detection tools to provide more insights for operators to be able to take a better action or more timely manner of action in response to those fluctuations. So a brief introduction to the technology itself. Sentry is a low maintenance bio-electrode sensor. It basically consists of 2 electrodes, an anode and cathode. A biofilm is formed on the anode side. Specifically, geobacters are formed on the sensor. So as the water streams through the sensor, it will consume the organic matter and respire electron to the circuit. We basically measure the current of these electrons, and that is providing insight about the activity of the microorganisms in the system. And we are sending these data to our dashboard, which are shared with clients, and they can see the real-time data. As Pat mentioned, we are currently applying a threshold methodology where we evaluate if signal is exceeding a certain amount or it is below a certain amount. Basically, the high alarm is likely suggesting that there is overloading happening in the plant, and a low alarm is basically showing a biological upset. It can be a low flow or it can be a toxicity event. This methodology is working for us. We are able to identify some events. However, we are going to use more advanced techniques to be able to improve the efficiency of the method. So what are the goals? Basically, we want higher accuracy. We want to identify more events and potentially reduce the false alarms. The algorithm that we are going to use should be adaptable to changes, because as you know, wastewater influent changes over the time, and it can have different structures, and it can change, and the structure might be changed over the time. So it should be adaptable to those changes. And it is important to raise the alarms quickly so that the operators can take actions effectively. So timeliness matters, and it should be easy to read. So it should be interpretable as well. Additionally, we should recognize that we have different patterns in data, and it is important to capture different patterns. That is one thing that we cannot do with our threshold analysis. I added some sample of different patterns that we usually have. We might have random spikes, like if you plant a microphone in an environment. We might have basically a constant baseline with the slight increases. We might have increasing or decreasing slope. We might have fluctuation in the signal. We might have a sudden jump in the signal, which remains in the new baseline, and we might have some random spikes. So it is important to identify different patterns and basically raise alarm based on those changes. We do have different event detection methods. The most simple one is using simple statistical analysis, using moving average, using cumulative sum. But these are very limited from case to case. If the signal is outside of the expected statistical range, it cannot identify the events. Furthermore, these are not suitable for the signals with a non-stationary environments. So it is not going to be very effective in influent wastewater. The second type of the event detection methods is combination of set points, which is similar to the method that we are currently using. It requires prior knowledge to the system, and it might not be able to capture the complex changes or structure changes in the signal. That is why we are focusing on the final time series forecasting. And by this, we are able to capture complex relation or complex structural changes in the signal. And we identify that these kind of methods are going to be more effective in influent wastewater event detection. Before jumping into the methodology, I would like to go over some definitions just to ensure we are on the same page. So we have outlier, which is a few timestamps that are inconsistent with the background. And we have events. This is important to differentiate between these two. Events are cumulative outliers or various outliers that accumulate and create a sustained anomalous period. So we don't want to raise an alarm whenever signal have a sudden spike, which is very short. We just want to raise an alarm when something rare is happening and something is actually affecting the signal. And also we have a baseline change, which is a change in the baseline. So initially it is an event, but after a certain point of time, we don't want to raise alarms continuously. And also we have false positive, which is where we are raising alarm, but no event is actually happening. We have false negative, where an event is actually happening, but the algorithm is not able to capture them. And finally, a metric that we use to evaluate the effectiveness of event detection model is precision, is basically number of captured events divided by total alarms that were raised by algorithm. So here is an overview of the methodology that we are going to implement. We have the raw signal. It can be in real time or it can be historical values in offline mode. We basically use a moving window to that basically enable us to use the most recent values. And also it will help us to replicate the online implementation of the system of the algorithm. In each moving window, we do a prediction, and we then compare the predicted value and measured value, which give us the residual. This residual will be used in outlier classifier, where it is basically compared with the outlier threshold, and the output of it will be a binary array. The outliers are going to be 1, and background data is going to be 0. And then we feed this output to event classifier. That is where we differentiate between outliers and events. If we have consecutive outliers, numerous outliers within the window, then we have an event. If not, it's just an outlier and we don't raise an alarm. As I mentioned, we are using a sliding window. The window slides by one interval. And in each window, we do a couple of steps. The first step is data reduction. We basically change the default interval of sentry signal, which is 1 minute to 15 minutes. This has been done to just reduce the data points and increase the computation efficiency. And also it smooths the signal a little bit to reduce the false alarms. And in step 2, we basically take the window and we separate the last variable, which is a target of prediction. We just do that to ensure we don't have a data leakage. We don't want to have target in the values that are used for the prediction. And as I mentioned before, after prediction, we compare the predicted value and the actually measured value, which give us the residual. I will go through the methods that we use for prediction. And finally, we compare the residual with the threshold that give us which indicates whether the final variable in the window is outlier or not. We do have 2 models for prediction. The first one is Sentry Model 1. It is based on linear predictive coding, or LPC, which is considered an autoregressive model. It is basically using the historical values and multiply them by coefficient to estimate the most recent measurements. It is primarily used in audio and speech processing applications to encode and decode speech signals. So what really matters here is to calculate those coefficients To do that, we take the historical values in each window, and we apply a fast Fourier transform function to calculate the autocorrelation coefficients. And just to simplify this step here, we create a Toeplitz matrix of these autocorrelation coefficients, and solving them by recursive methods such as Levinson-Durden can give us those coefficients that we need. Then we multiply these coefficients by the historical values, and we have our estimated or predicted value. The second model, Sentry Model 2, is based on Facebook Profit Model. It is an open source algorithm that was developed by Facebook. It basically is a combination of three different functions: a growth function, which is evaluating the change points in the signal. These are the moments that trend of the data is changed, and also it is just considering the non-periodic changes. It has additional second function, which is basically using, again, a Fourier transform to identify seasonal pattern and weekly pattern, also diurnal patterns. And also, finally, we have holiday function, which going to include the impact of specific dates, which we know that might affect the wastewater influence. And finally, for differentiating between those outliers and events, we are using binomial event discriminator, or BED. BED is basically evaluating the probability of event happening based on number of outliers. So it has a separate window. It slides through the outlier array, a binary array, and it is calculating the probability based on number of outliers within each window. And if it is exceeding the BED threshold, it is declaring those outliers as events. Otherwise, those are not events. And finally, for our case study,
Cash, can I jump in here, Cash, just quickly?
Sure.
Can we, this is maybe a good break. So now that you've gone through technically what we're doing and how we're analyzing these data sets, before we transition into the case study, which for me is the most important or most interesting part, do you have poll questions that you want to put up? And
yes, and can you run the whole one?
Sure.
So select the environmental or collection network factor that you have had experience that causes the most issues for wastewater treatment facilities. INI is 1, industrial discharge, landfill leachate addition, ferric addition, and fog. So if anyone has any experience with any of those things causing them actual problems at a wastewater treatment facility. Yeah, we would assume that industrial discharge would be the most common. From our experience at Sentry, inflow and infiltration, it's crazy. When we go to clients normally, it's usually, oh, it's definitely that industry is causing us problems. And then we actually find that INI and stormwater events really do impact treatment performance. And we've certainly had a few landfill leachate additions, people receiving landfill leachate at lift stations, or just haulers arriving with loads. That certainly cause issues as well. Okay, let's end that poll. Love it.
So we, as I mentioned at the beginning, we have a case study of ton of Coburg here to test the models, or the event detection models that we are proposing. As I mentioned, it is a mid-sized municipality wastewater treatment. One Sentry system was deployed at this plant. And this plant is basically receiving average of 6.5 million gallons per day of wastewater. The Sentry, awesome. So the Sentry is installed after primary clarifier, right before the aeration tanks. And we have average of 500 milligram per liter for COD in this location. And the sensor was installed on August 18th. So we are using almost more than 3 months for this case study to test the models. Here is the general plant data. As you can see, we have there are no structure in the signal. We do have 4 different types of event happening in the plant. The main one was low flow events, sharing 55% of total events, and it is shown by orange marker in the plot. And usually it appears as a drop in the sentry signal. And the next event type is industrial discharge events, which are shown by blue marker in the plot. Usually it is a drop in the sentry signal, but we have 2 industrial discharges events that were an increase or sudden spike in the signal. These were likely indicating that organic loading rate was increased, but the other ones likely suggesting that there is a toxic compound coming into the plant during these events. Also, we have precipitation or heavy rain events, which again appears as a drop in the signal. And we have other events which are associated with any process change or any signal cleaning. Both of them are shown as green in green markers, and both of them are drops in the signal. So for our conventional threshold strategy, what we do is basically we take first 2 weeks of data, we calculate the average and the standard deviation of the data during those periods, and we set the threshold 2.5 times standard deviation above and below the average. And this 2.5 is based on our experience. That is the value that we usually use for our municipal clients. After that, every time the signal exceeds the higher threshold or is lower than the lower threshold, we raise an alarm. With this methodology, we were able to capture 11 events. And however, on the other side, we had 26 false positive events, and we couldn't capture 20 events out of 31 events.
Do you mind if I just make a comment here, Kash?
Sure.
So this is, yeah, as I understand it, this is the full data set, or this is the data that was analyzed for this client. And what we're measuring here, just so everyone understands, sentry signal, it's correlated to consumable BOD, milligram per liter. So basically the client in this case wants to understand when the wastewater entering the facility has BOD that's in excess of 300 milligrams per liter, because clearly that's an organic overloading event, or when the capacity of the biomass to consume that BOD is lower than the equivalent of 100 milligram per liter. So when the signal typically goes above or below those alerts, it means that the plant is likely not going to be able to treat the wastewater to the appropriate standards. And that's why just normal threshold alerts do make sense. It's okay, well, if the wastewater coming in is really concentrated, okay, we need to know about that. If the wastewater coming in is stopping our biomass from actually doing its work to a certain extent, that's the low end alarm, we need to know about that. So that's why those high and low alerts typically make sense.
Yep, thanks, Patrick. Yeah, so these thresholds are set manually by our client managers, and it should be changed manually again. So if we have a drop in the baseline, unless the client manager doesn't change it, it stays the same and it will raise alarms. That is why I didn't change the threshold to just test how many false positives it will produce. So we are aiming to increase the precision of this strategy by implementing automated models. So for model 1, the first step is identifying the proper window size. What really matters here is the precision and accuracy of the prediction, and we define the proper window size based on those. We use 2 metrics, R-square and RMSE, to evaluate the prediction efficiency. And as you can see, we expect to have a better performance when we increase the window size, because basically we are using more data to predict one timestamp ahead. However, we have to maintain the balance between the computation time and efficiency, because as we increase the window size, we are increasing the computation time. As a result, the optimum window size will be the lowest window size that we have a stable performance, a higher R score and a lower C. So here we chose 288 data points with 15 minutes interval that will translate to 2.5 days. So we are using 2.5 days of most recent data to just predict the current timestamp. And here is the prediction results of model 1. For the window size, we used the 3 weeks of data, and the R score of the model is 0.96, and our RMSE is 7.95, which is acceptable comparing the based on the range of the signal. You can see it is aligning pretty well, the predicted line and the centricity, actually measured centricity line. And we have residuals here, which are difference of the centricity line and predicted value. And we can see we have some spikes here. And these are the outliers based on the comparison of the residual and outlier threshold. And after implementing the BED to classify outliers or classify events, this is the final result. We were able to capture 18 events, which was an increase from 10 compared to the conventional threshold strategy. We had slightly more false positive from 26 to 29. And since we were able to capture more events, of course, we have less false negatives, or the events that wasn't able to capture by the algorithm. And the final precision was increased from 0.23 to 0.42 by applying the model 1. And as you can see here in the middle, for example, we couldn't capture these low flow events, because basically they were in the same standard deviation of the rest of the signal. They were just local drops in the signal. So we are able to, by implementing this new model, we are able to detect these ones as well. And the preliminary results of the model 2. This is still a work in progress. We are going to sync it with BED as well to identify or classify the events. But I just wanted to show you the preliminary result of the model 1 and see how it is working on the data set. So the dark markers or circles are actually measured sensory signal, and the blue line is the forecasting line by model 2, and the light blue is showing the 95% confidence level. As you can see, in response to different changes based on the significance of them, the algorithm identifies these red lines, which are change points, or the points that the trend of the signal was changing. So if the event was significant, or we have cumulative events, then the signal trend was changing. So this is promising for us. It seems like it is correctly identifying the trend and changes in the structure. And we are hoping that using this model will reduce our false alarm even further. So Selena, can you run the second poll, please?
Thanks, Selena. Okay, so I assume people can see this. Which of the following is not a benefit of real-time event detection? Oh, that's like it's not a benefit. Okay, so it can provide immediate warning of abnormal events. It can replace the regulatory sample procedure. Yes, that would not be. It can detect different types of patterns. Yes. It can improve the precision of alarming. Yes. Good. Okay, we're all in agreement here. Okay. Yes, this is not for replacing regulatory sampling procedures. This is for helping customers detect in real time, perhaps before things happen, when wastewater conditions entering the treatment facility are not appropriate for successful treatment. Okay, love it. Okay, I will end that poll. Okay, thanks. Yeah, take it away, Kash.
Thank you, Patrick. So just going through the results, why applying this new methodology actually matters is that we were able to increase the precision of event detection from 0.23 to 0.42. We were able to identify wider range of patterns, even if it is local, even if it is not a significant change in the signal. We are able to identify that event with the new model. Also, I have a chart here that shows you in each type of events how we could perform better with the model 1. Basically, we were able to detect 10 events in low flow events in the new model compared to 6 events in the conventional threshold strategy. Also, in industrial discharges, we were able to identify 5 of them instead of 3 in conventional threshold. So it is actually having a better efficiency. And just to conclude the presentation, we are increasing the precision. Again, it is automatic, so it is reducing the workload of client managers. It is real time, so we are able to share the actual real-time results with the client. For that new feature, we are going to use Azure infrastructure. So our sensor is currently being sent to IoT Hub. From there, we can apply Azure Function, which is a tool to apply Python algorithms inside the Azure, process data, apply the algorithm, store the results, and visualize it with Power BI and share it with client. So client has immediate access and receives immediate alarms from these novel algorithms. And also, we are working on a framework for connecting Sentry panel to autosampler. And we are going to connect that framework with the new models that we are developing. It can basically eliminate 90% of manual sample analysis. Again, it shouldn't stop regulatory sampling, but potentially it is shifting the sampling to event-driven samples instead of daily samples, which can be time-consuming, costly, and labor-intensive. So we are interested to partnering with you. So if you have a case study or if you have a problem statement of detecting toxicity, smart controls, smart decision makings, or optimization in AD or aviation, we are looking forward to working with you. And finally, special thanks to our research partners at UIUC, Dr. Rokozik and Ariane Mohamednejad. And also I would like to thank Dr. Rakesh for his contribution to this project. Thank you very much for your attention. I'll be happy to answer any questions.